an incredibly important topic for A-level physics is dimensional analysis. Now, this is actually part of the A-level physics specification, but for reasons I'm not sure of, it often gets overlooked, and yet it's such an important skill. And if it were up to me, this would be taught at GCSE level, because it really underpins what physics is all about. So it's so important to have a clear understanding of dimensional analysis. Let's have a look at dimensional analysis then. Any quantity that can be measured in nature, any quantity can be broken down into 7 base dimensions, and they're listed here: time, length, mass, electric current, temperature, amount of a substance, and luminous intensity. And the letters that are given for those dimensions, and they're all capital letters: T for time, L for length, M for mass, I, capital I for current. This is a capital theta for temperature. Can't use T because we've always used that for time. N for amount of substance, and J for luminous intensity. Now, each of those dimensions has a base unit, what we call a System International, or SI unit. This is what the entire scientific community has agreed to use. So times will be measured in seconds, with the lowercase s as the symbol for that unit. Lengths in meters, masses in kilograms, currents in amperes or amps, temperatures in Kelvin. You can use degrees Celsius as well. Amount of substance in moles. And finally, luminous intensity in candela. But we're not going to be using luminous intensity really in A-level. I can't think of any time where I've seen it. I've seen all the others used, but not luminous intensity, so we'll tend to concern ourselves with the first 6 of these base dimensions. Now, some quantities are combinations of these. An area is 2 lengths times together, and so on. But you can't express any quantity that can be measured without it being some combination of these base dimensions. Now, from a physicist's perspective, some of these are a little bit bonkers. Temperature, for example, can be expressed in terms of the others. It depends on your interpretation of entropy. Same with the number of moles of a substance, the amount of substance. Does that need to be a dimension? It's just an amount of something, it's just a number. And luminous intensity is a similar situation. So some of them can be expressed in terms of the others, but it depends on fine differences between, let's say, chemistry and physics. So these are what the whole scientific community has agreed with, mainly to satisfy those damnable chemists. So here we go. Dimensional analysis. A few principles. The most important principle is that of dimensional homogeneity. Something is dimensionally homogeneous if the dimensions are the same on both sides of an equal sign. Now, there are times in physics where we're quite happy to break that, where we've got certain constants we set equal to 1 for convenience sake, but we will not be dealing with those until you're studying physics at university, so don't worry too much about that at the moment. You cannot add quantities that are not dimensionally homogeneous, and you cannot subtract quantities. That doesn't make sense. If I say to you 30 centimeters plus 5 seconds, I can't process that. That doesn't make any physical sense. You know, what's 7 kilograms plus a meter? It doesn't make any physical sense. But 2 kilograms plus 3 kilograms is 5 kilograms. That's fine. That makes a lot of sense. We can add masses to masses. We can't add masses to times or to lengths. It doesn't make any sense. So for clarity, when we use dimensions, or indeed when we use units, we can use square brackets just to make it clear that the letters we are writing are not equation symbols. That's important. M, for example, could be mass, but the unit with a lowercase m as its symbol, the meter is a unit of length. And you can see here I've given a few other examples, displacement and the unit of time and period and the unit of temperature, or the dimension, should I say, of temperature, capital T. So we do need to be a bit careful. We tend to use capital letters for the dimensions, and units often have lowercase letters, but not always. Kelvin, for example, is a capital K, joule is a capital J, Newton is a capital N, Coulomb is a capital C. Now I come to think about it, we use a lot of capital letters for units, so maybe I shouldn't have said that complete nonsense. I'm not editing it out. Right, so what do we do when we analyse our dimensions? We would prefer not to use slashers if we can help it because of the ambiguity. We prefer negative powers. We can use the bullet operator, that's a dot halfway up, not a dot near the bottom of the line, that's a decimal place or a radix point with base 10. We'd prefer to use a dot part way up. That indicates a multiplication between scalars, or indeed a scalar product between vectors, but that doesn't matter. So meters per second is a unit. If I'm saying it's a unit, I could put square brackets around it for clarity, and it would prefer to be written like this. We can use a dot. Sometimes that can make it clearer. It's not really needed. The places where this becomes important is things like the unit for specific heat capacity, the joule per kilogram per Kelvin. You can write that like this, or you can write that like this, but you can't write that like this. It doesn't make any sense because, as we've already studied, the order of operator precedence, this would be joules multiplied by Kelvin and divided by kilograms, because multiplication and division, even if it's implicit multiplication, it doesn't matter. However, very often exam boards actually prefer this unit of specific heat capacity and dislike this unit of specific heat capacity, even though this one is correct and this one is incorrect. It's frustrating, but it's the way it is. So let's get rid of ambiguity and use negative powers. That everyone's happy with negative powers. Joules, kilograms to the -1, Kelvin to the -1. No one disagrees with that. We're happy with that. Although perhaps I'd put the kilograms in brackets and raise it to the -1, because you wouldn't want to think the kilo isn't raised to the -1. Don't worry about that. That's just me being super weird. So, dimensions of quantities. There's a displacement, there's a time. The dimension of a displacement is a length, and that can be expressed like this. That's the product of all 7 dimensions with powers. Now you'll notice that all except length, the power is 0. The power for length is 1. That gives you your L dimension. Fine, okay. We could do the same thing with time, which is dimension of t. All the other powers are 0. And a velocity, all the other powers are 0, except length, which is 1, and time, which is a power of -1, -1. Because velocities, speeds, are lengths divided by times. It could be quite useful to write this, but I wouldn't be writing things like luminous intensity, amount of substance, temperature, electric current. I wouldn't be writing them if there's no way that's ever going to be involved in the quantities that I'm investigating, because it's just a waste of time and it actually makes it even more confusing and untidy. So, I will go back one slide for a second. That last sentence, if you raise anything to the power of 0, it just gives you the number 1. But that number 1 doesn't have dimension, so effectively we've got rid of the dimension. Right, so let's take some more exciting, or I've called here more exotic quantities, things like forces. Well, let's pick any old equation for force, F equals ma, and we can, instead of writing it as F equals ma, we can look at the dimensions. Well, the dimension of m is easy. It's a mass, so we can put that in square brackets. The dimension of a is a little bit trickier. Accelerations are lengths divided by the squares of times. If you get confused, remember the unit for acceleration, meter per square second. So there's our dimension, and we can put these together in the order TLM. I'm not going to bother writing all the other dimensions. That is the dimension of force. T to the -2, L to the 1, M to the 1. Nice and easy. Do the same thing for energy. Pick any equation for energy. Well, we could pick half mv². We could pick mgh. It doesn't matter. We could pick force multiplied by displacement. And we already know what the force is here. So if we're going to do force multiplied by displacement, we're just going to have another L. So this becomes t to the minus 2, L to the 2, m to the 1, which is exactly what we get. When I got there by using mgh, m is a mass, h is a length, and g is the acceleration due to gravity. And we already know what acceleration is because it's come from there. It gives you the same dimensions regardless of how you derive them, whether you use half mv², mgh, or work done equals force multiplied by displacement. It doesn't matter. It gives us the same dimensions, as well it should. So here I've got half mv² analysed as well. Half doesn't have dimensions. It's just a number. There's no dimensions with it. So don't be confused when you get things like that coming up. Just leave it blank. Mass is mass, and this is the velocity squared. So the velocity was length time to the minus 1, but we've squared it. And now when we multiply this all out, we end up, well, look, it's all the same. That is the dimension of energy. Now let's get something much more exotic. So this is Coulomb's law. It tells you the force between two charged particles. Q1 and Q2 are the charges of them, and R is the distance between them. We've got this constant, 1 over 4 pi epsilon naught. Force is just a number, pi is just a number. But what about epsilon naught? Perhaps we're interested in the dimension of epsilon naught so we can figure out what unit to give it, or understand the physical nature of epsilon naught. The first thing we're going to do, we could take our equation, and we're going to rearrange it so that epsilon naught is the subject. Now we can do that comfortably because we've been practicing our algebra. Then what I'm going to do is put our dimensions in. Q1 has dimensions current times time. Q2 has dimensions current times time. The number 4 has no dimensions. So that's no dimension raised to the power of -1, it's just nothing. We've then got pi, no dimensions. We've then got r², that's a length, but it's to the -2 because it's on the denominator. We've then got force, and we already know what force is, and that's to the -1 because it's on the denominator. Now we just combine them all. What have we got? 2 i's, that's I to the power of 2. How many t's have we got? We've got 1 t there, another t there. These t's are to the -2, but they're also to the power of -1. So that becomes t to the 4 in total. T to the 2, t, and t is t to the 4. And L to the 1, that's actually to the -1, so that becomes L to the -1, and L to the -2, altogether L to the -3. So we now know the dimensions of epsilon naught. Now, why would we ever want to do that? Well, one way is to check equations are right. And that's an important thing to be able to do, especially if you're coming up with equations yourself or you're half remembering things. Why else would you want to do it? Well, you might want to do it to convert units. That's such an important skill. Or maybe even to derive equations for yourself. Brand new equations that have never been given before. So we're going to go through, we've looked at checking equations. Let's have a look at a few others. Let's have a look at converting units. How do we use dimensional analysis to convert units? Well, let's convert a length into inches. It's an older unit, but it still does the rounds. 1 inch is 2.54 centimetres by our modern definitions. So if we wanted to convert a length of 5.5 centimetres into inches, then I need to do something to that length without changing what it is. Now, you can multiply any quantity by the number 1 and it doesn't change the quantity. As long as the number 1 has no dimensions, no direction, none of that, as long as it's just the number 1, it doesn't change anything. So the thing represented by 5.5 centimetres, that's a physical length. If I multiply that by 1, I have not changed that physical length at all. Well, we have said that 1 inch is equal to 2.54 centimetres. That is equal to. which means that 1 inch divided by 2.54 centimetres is equal to 1. Great, let's times by 1 inch divided by 2.54 centimetres. Now the centimetres cancels on both sides of the equation, and I am left with 2.17 inches. There's a little note here about rounding. In our calculation, we used 5.5 centimetres. That's 2 significant figures. So we should have rounded our answer in the end to 2 significant figures. But we might keep 2.17 inches rather than just saying 2.2 inches written down, so that if we have to use that in any subsequent calculations, we'll use the unrounded number, or at least the less rounded number, because that's going to reduce the risk of accumulating rounding errors. We don't want rounding errors if we can help it. Here's a unit conversion that is first met usually at the very beginning of year 12. We know that joules is a unit of energy, but there's another unit of energy called the electron volt, and you become convinced that 1 electron volt is equivalent to 1.60 times 10 to the negative 19 joules. 13.6 electron volts, which is the ionization energy of hydrogen, that's in the ground state. How do we ionize, or how many joules do we need to ionize that hydrogen? So we need to multiply 13.6 electron volts by the number 1. What is that number 1? Well, it's going to be this way around, so that we're cancelling out the EV and leaving just the unit of joules. So that's a fun little way of converting. It's important to lay it out clearly so you don't get confused. It says here, you're multiplying a length by, you're dividing a length by a length. So the quotient, that's what you call it when you have one number divided by another, of two lengths, is going to be dimensionless. It's also going to be equal 1 if the two lengths are equivalent to each other. The quotient of 2 times is also dimensionless, and so on. So that's just saying what we've already said. So here is a really fun conversion. This is Pascal as a unit of force to pounds per square inch, PSI. And that's pounds force per square inch, not pound mass per square inch. Imperial units were very funny things. Well, what's a Pascal? It's a Newton per square metre. Fine. So we need to get rid of some of this, don't we? Let's first of all get rid of the newtons. We know that 1 pound force, we're given the conversion. We want to cancel the newtons, so we multiply our number by 1 pound force divided by 4.45 newtons. That's just the number 1. The newtons cancels. In terms of lengths, we want to get rid of the meters squared. Well, I've got a conversion into inches, but that's for centimetres. Well, 1 metre is 100 centimetres. That allows me to cancel one of the metres, but if I square all of that, I'm able to cancel both of the metres. And then I do the same thing to cancel the centimetres and give me inches. And if you express all that using numbers, you end up with 14.7 psi. You'll find at petrol stations and things, the unit psi is still used for pressure in tyres. So it's not a dead unit, it's just an old unit. Right, so here's a fun use of dimensional analysis. Deriving equations. So if we want to derive the drag, the fluid drag, on a sphere moving through a fluid. So it's like air resistance, but it might not be air resistance. It might be water resistance or oil resistance, or it could be air resistance. We have to first of all think, what does it depend on? Well, it depends on probably the size of the sphere. Maybe we can say area, maybe we can say diameter, it doesn't really matter. Probably depend on how fast the sphere is moving relative to the fluid, and the density of the fluid might have some effect. We think that's what it depends on. Well, the dimensions of all those quantities are there. Density is a mass divided by a volume, so that's expressed here. I've kept the t's here because I think, and the m's where there's zeros, because I think that'll make it clearer. And we think the equation, it's not going to quite be an equation because we don't know what the constant of proportionality might be, but we think that force is going to be proportional to something to do with diameter, something to do with velocity, something to do with density. And I've used A, B, C as those powers. Let's calculate what A, B, and C are. So we can first of all write out our dimensions. There we go. Exactly what we had. So instead of writing the equation, we put that the dimension of f is that, and that has to be equal to. If these are proportional, then it has to be equal to. This is the dimension of the diameter of the sphere, which is just L, to the power of a, because diameter to the power of a. And this is the velocity, L divided by t, to the power of b, and so on. So now what we're going to do is try to find out what a, b, and c are. It's a puzzle to solve. It's not a difficult puzzle to solve, really. We could look at mass first of all and say that must be homogeneous. And this term has mass in it, and this term has mass in it. And so, because this term is mass to the 1, then c must be equal to 1. And then we could look at another quantity. Let's just pick one. Let's pick temperature. This is 0, this is -1, that's 0, that's -2. So b is going to have to be 2 to get time to the -2 on the right and time to the -2 on the left. And then finally, we can look at length. And we go, well, there's -3 and 1 and 1. So at the moment we're on the right-hand side. Well, what are we going to have to do? We're trying to change A, aren't we, here? So let's worry about A in a second. We've got 1 here. We've got 1 there, so that cancels. We've got -3 there. So I need to have more than that. I need to have another 2 of these in order to get to where I need it to be. So that means A is going to equal to 2. And you could double check this. 2 lengths. Add another 2 lengths. That's 4 lengths. Subtract 3 lengths. So that's going to be 1 length, and that's 1 length. So you can double check. If you get lost, you can double check. Don't forget to raise L to the 1 to the power of 2, so that becomes L2. Okay, so that gives you your numbers, which you can then plug into your equation, or your proportionality anyway, and you get that. So it looks like drag is proportional to the square of the speed that a body moves through a liquid or a fluid. But what about viscosity? Well, we could do the same thing again, but this time let's consider viscosity instead of density of the fluid. The dimension of viscosity is given here. There's our equation. We can use it in the same way as we did before. A, B, and C, these are the dimensions for those quantities. And we can use that with some basic equations to figure out what A, B, and C are. First of all, let's look at mass, because mass only appears on the term with the power C on the right-hand side. And so C equals 1, and then just unravel all the rest of them. And the equation therefore looks like this. Ah, that's interesting. So now it looks like the drag force is proportional to the speed. But before, it looked like it was proportional to the speed squared. How interesting. So what if we do it for both viscosity and density? Well, that's where it gets a bit tricky. So we've now got an equation like this, which means there are 4 terms after the proportionality sign. We're using both viscosity here and density. Viscosity, remember, is basically it's an indication of how difficult it is for the fluid to get out the way as something moves through it. So that feels like it should be relevant to this. So there's our expression. Now the problem with this is, if we try and write down some simultaneous equations for time, length, and mass, which we've just done there, we've got a problem. There are 3 equations because there are 3 dimensions that are relevant, but there are 4 unknowns. That means there's more than one solution. Infinite number of solutions. So A, B, C, D, what I've done here is I've just said that there are -2 times on the left equals A, there's no time there, so -1 lot of B, -1 lot of C, and there's no times there. So that's how I've got that equation, and I've done it with the other 2 as well. Now this is a problem. 3 simultaneous equations, 4 unknowns. But we can find solutions, we just have to do a bit of guesswork. So we could, for example, just guess that because -2 equals -b, or should I say minus b minus c, that maybe B and C add together to make -2, so maybe that's going to be -3/2 minus a half, which is what we have there. Or we might start from the third equation there. 1 equals c plus d. Well, maybe c and d are just a half each. That would work. Why not? So we can try some things. We can get a solution by doing that, which you can see we've got there. I think it's the same slide as last time. Yes, I should have deleted that slide. We have the same thing. We get a new equation like that. We can plug those powers in, and we get something that looks a bit like this. You can actually get to that equation just by multiplying together the previous two equations, actually, and that's how things should work. The drag force for density and the drag force for viscosity. You just times it together, you can get this equation. We still don't know what the constant is. So this works dimensionally. It might not be right, of course, but dimensionally it works. So that's fine. All three of those are dimensionally equivalent. They are homogeneous. Which one we use becomes a matter of physics or maybe even engineering. It's something we have to think quite carefully about. Very often we're actually going to use this equation. Not always, but very often we're going to use that equation where we say that the air resistance is proportional to the square of the speed that something moves through the air. But not always, and in fact the first equation appears in the turning points option of the AQA physics A-level. It's Stokes' law for viscous drag, but we're not going to talk about that during this session. We're just looking at dimensional analysis. I've included this problem now, the Galileo study of whether giant animals are possible, because this often gets described as a use of dimensional analysis, but we don't really need to see it that way. We could just have a look at some basic ideas. You don't need dimensional analysis for this, really. Yes, we can have giant animals, but it doesn't just look like a giant ant from that old sci-fi thriller film Them, which is where this slide comes from. I'm hoping I've got fair use rights to use this slide, or this screenshot of a giant ant in Greyditch in Fallout 3. Again, I think this is fair use. So let's just consider animals with bones. Let's just consider animals with a femur. And it's fair to say that the size of the animal is probably going to be related to the length of the femur. And I'm going to use the lowercase l. Curly L is how we write that, so we don't get it confused with the number 1 or the capital I. So that's a curly L for the length of the femur. The diameter of the femur has probably got something to do with how strong the femur is, and that's probably going to be important. So let's have D as the diameter of the femur. So we reckon that the strength of the bone is going to be related to the area of the bone, the cross-sectional area. We also think that if the bone is more massive, it's probably going to be stronger as well. The height of the animal is going to be related to the length of the femur. The mass of the animal is going to be related to the mass of the femur. That kind of makes sense. Mass of the animal proportional to the volume of the animal, and therefore the volume of the femur. It all kind of makes sense. And so the volume of the animal is proportional to the volume of the femur. So we're kind of just having some guesses at things to do with these giant animals. And then we can have a look at the relationships. So we want the bone to be strong enough to support these animals. Some set constant amount of strength of bone that is sufficient. So let's just call that S and say S is proportional to D squared. That's what we had before on that list. The mass of the animal is going to be related to the volume of the animal. Of course, it's going to be the density multiplied by the volume of the animal. But that's going to be related to the volume of the bone. So that's L squared. It's related to L squared. It's not exactly going to be L squared. Probably going to be more like sort of LD squared. But it doesn't matter. We're just taking this as a rough idea to get the dimensions. And then we can say that the strength of the bone is related to the mass of the bone. And if we chuck these ideas together, which we can do, you can see there, we've got an M here and an M here, we've got a D here, we've got an S here and an S here. We can put these equations together. The constants, I don't know what they are. it doesn't really matter. They're just turning things from proportionalities into equations. So we can combine the equations, then we can combine the constant, and you end up with something that looks like this. L cubed equals CD squared. Now this isn't just animals, we do this with buildings. If you increase the height of a building, you have to increase the area at the base of the building to keep it strong. And we use this law we're now currently deriving all the time in engineering. And so you can see L is proportional to D to the power of 2/3, or D is proportional to L to the power of 3/2. It's just working with these powers, and the constant is changing accordingly as well. And we can do some comparisons. We could say we've got two animals with the same basic shape and the same strengths of their bones, and the same basic shape means that C is the same. Then we've got animal 1 here and animal 2 here. And if we divide one equation into the other, you get this. And the constants cancel out. That's convenient. And that's dimensionally consistent because either side of the equal sign has no dimensions. And you can take the powers outside. And you can do things like this. So we can now see the relationship between the ratio of heights of animals and the ratio of widths of their legs. And it's not a proportional relation. Well, it's not a linear relationship. We could make the diameter of the femur, so the diameter of the leg, the subject, and see how that's related to the height of the animal, or the length of the femur. This is called the square cube law, and as I say, it works for animals, but it also works for other things as well. It means the taller it gets, the leg diameter has to get larger, but not in a linear relationship. So let's look at an example. If I want an animal that's twice as tall, the leg ratio is going to have to be 2.8 times, almost 3 times the diameter of leg for the animal to be twice as tall, but still have the same strength of bones in the leg. If the length of the leg is 3 times as tall, so 3 times as high the animal, now it's going to have 5.2 times the diameter. So how do we address this? Well, we don't have the same basic shape of animal. We don't. That's why elephants look very different from ants. But with buildings, this tells you why you have to have a much wider base if you're taller, or do some very clever engineering tricks. And that's everything I wanted to talk about with dimensional analysis. This QR code takes you to some Isaac Physics questions, if the link is still working. If Isaac Physics has moved some things around, it won't work, but you can find those questions yourself. So have a crack at those, and then we can move on to the next topic.